So the number of attributes is essentially the dimensionality of your data, of your problem that you are dealing with. So that is an important aspect to keep in mind. So if you wanted to visualize multidimensional data, how that is possible? So that is one important questions to be addressed. Say, for example, you have a 10-dimensional data. How can you have a holistic understanding about the distribution of this 10-dimensional data? So that's a very challenging thing, because you cannot straight away visualize beyond 3 dimension, even though there are few tricks to represent things in 4D, but not great. So just to give an understanding about the visualization purpose. So we have these visualizations about uh, a line in one-dimensional aspect, a square in a 2-dimensional aspect, a cube in a 3-dimensional aspect. Typically, we are comfortable with 3D visualizations at the maximum, but there are also extensions of 4 dimension, which we refer to as tesseract, though it is not very intuitive to understand, but there are studies about tesseract. So 3D is what we are usually comfortable with. So if we have a 10-dimensional data, that means you are dealing with 10 attributes. How to understand or visualize the data? One aspect can be feature selection. And what do we mean by feature selection is this. So if you have 10 attributes, out of that, pick 3 attributes and then visualize it. Then you will be able to visualize 3 of its features. Then pick another 3 features, then visualize it. So in that way, we can take a subset of the features and then you can visualize in 3D, but that doesn't give us a complete understanding about the distribution of the data that we are dealing with. So in that case, we have to go to this concept of dimensionality reduction. The core intuition behind dimensionality reduction is that a 10-dimensional data can be reduced to a 3-dimensional data, preserving all the useful information of all 10-dimensional data. So that is the important point. If we are doing feature selection, we are only taking 3 feature subsets. So we are totally kicking out the other 7 dimensions. So we are not having any holistic understanding. But in reduction, it is preserving the useful information from other dimensions and it reduces the dimension. So that is the beauty of dimensionality reduction. So we will get to a bit more understanding of what does that mean. And in this context of dimensionality reduction, apart from visualization, we also mentioned that it helps in reducing the complexity of your problem. And now, what does it mean? What kind of complexity does it reduces? Let's try to understand that as well. So before that, let's take a look at an important result from um, a field of mathematics called hypergeometry. So we are going to discuss a useful result from the domain of hypergeometry. That means geometry in higher dimensions. So let us first assume a square, the unit square. So by unit square, we mean we have a square. The width and height, they are of 1 unit. The unit can be centimeters, inches, even kilometers. So that is left to us. So, but it is a unit square. That means 1 unit. So in this unit square, let us randomly pick 2 points and then find the distance between them. Let's take another random 2 points, find the distance between them. Again, pick another random 2 points, find the distance. The distance in the sense you are finding the Euclidean distance between them. So here we have picked 3 random pairs, but you can think of more number of, say, increase these experiment, maybe like 10,000 times. And we will have 10,000 distances. and now you average all the distances. So the average distance between any two randomly chosen point inside a unit square happens to be 0.52 units. So this is a mathematical result. So the width and height is 1 unit, but the average distance between any 2 points inside this unit square is 0.52 units. Let's extend this to 3 dimension. So in a cube, you randomly pick 2 points, find the Euclidean distance between those 2 points. So each point has 3 coordinates. So it's a 3-dimensional space. So similarly, maybe for example, do this for 10,000 times. So you have 10,000 distances. So here the width, height, and the breadth are 1 unit. And here also the average distance. So distance is specifically a single value. So the average distance is 0.66 units. So now when you increase one additional dimension, the average distance between 2 points also increased. That's the result we understand here. This is what we can visualize. But let us assume you have a 10-dimensional hypercube, a unit hypercube. Somehow you have 10 orthogonal dimensions. Let's assume like that. And then repeat this. So one point in a 10-dimensional space will have 10 coordinates. So you can find the Euclidean distance between any 2 points taken from a 10-dimensional space. Repeat this experiment maybe 10,000 times. The average distance between any 2 points in a 10-dimensional space is 1.26 unit. Each side is 1 unit, but now when you go to 10-dimensional space, it behaves a bit odd, something outside our typical logic. So we will think like the width and the height, they are 1 unit, and then the average distance between them is going beyond 1 unit. Even when you think about the distance of this diagonal, so that is anyway going to be greater than 1. So this is the average distance between any 2 points in a 10-dimensional space. If you further think about another extension, maybe a 100-dimensional hypercube, a unit hypercube, the average distance between any 2 points is 4.07. So what do we notice here? So the trend that we notice here is that as the dimension increases, the average distance between any 2 points is also increasing. To the other extreme, let us even think about like 1 million dimension. So in a 1 million dimensional hypercube, the average distance between any 2 points is 408.25. So there is a generalized result from this hyperdimensional geometry, where n is the number of dimension, and this equation tells us what is the average distance between any 2 points in an n-dimensional space. So this is the general equation. So if you look at these numbers, what do we infer? What should we understand is that the sparsity increases as the dimensionality increases. That is what we should interpret. Sparsity means points are not close to each other, but they are going away, apart from each other. So the sparsity increases as the dimensionality increases. So what is the problem if the sparsity increases? It imposes an additional challenge when you are dealing with machine learning problems like regression or classification. When you the important interpretation is that say for example regression, you are trying to fit a geometry that best represents the data. One important intuition to keep in mind that in machine learning, all the data that we talk about, no matter what, whether it is image data or video, the image data or text data or some time sequence data or tabular data, any data can be represented as a point in a higher dimensional space. So that is another geometric intuition that we should have. So we always think about our data set as a point cloud in some higher dimensional space. Say, for example, you are dealing with a classification problem and your task is classify as spam or non-spam mail. Let us give a color. Spam mail means red color. Non-spam mail means green color. So if we have training data set with us, it is going to be a supervised learning scenario. So we already know certain emails are spam and the other emails are non-spam. If we try to represent that as points in a higher dimensional space, we will see a cloud of points that are green color and a cloud of points that are red color. That is to represent these red dots are spam emails and these green dots are non-spam emails. And geometrically, what does a classification algorithm does? It will estimate a decision boundary between these two clouds of points, a cloud of point of green color and a cloud of point of red color. And classification problem is essentially finding a decision boundary that separates the green cloud of points and the red cloud of points. This is the geometric interpretation. So this can happen in any number of dimensions. Even deep learning techniques, they are trying to find these decision boundary. Any classification problem, support vector mission, it's trying to find a decision boundary. If you pick uh, linear regression or softmax regression, the logistic or softmax regression, it is trying to find decision boundary. So now, when the cloud of points are dense, then it is very easy to find this decision boundary. But if the cloud of points are not dense, then finding an appropriate decision boundary is a challenging task. So this is one place where high dimensional space can impose a challenge in solving a regression problem or a classification problem, because when you interpret that as clouds of points, those clouds or points are going to be more sparse, because average distance between any 2 points in a higher dimensional space increases. As you keep adding more attributes, the sparsity also increases. So that imposes a challenge. So if we say, for example, you only have 100 emails for training. Out of that, 50 emails are spam and 50 emails are non-spam. And let us assume we are picking some 10,000 unique words for classifying a mail as a spam or a non-spam mail. So if we decide 10,000 unique words, then we are dealing with a 10-dimensional attributes, 10-dimensional features. So we are essentially dealing with a 10-dimensional space. Each axis will be a word that we are talking about, which we considered as a feature. So if we represent these as a clouds of points, then there will be 50 points green color, which are non-spam, and there will be 50 points which are red color, which are spam. And it will be very sparse if we are considering 1,000 features. But at the same time, instead of considering 1,000 features, for example, if we consider only 500 features, then these points will become a bit more dense. If we consider 10,000 features, it will be more spam. If we consider 1,000 features, it will be bit more dense. If we consider 500 features, it will be bit more denser. So if we can come up with the denser clouds of points, we can solve that problem more robustly. We can come up with a decision boundary more robustly. If, let us say, you did not had this idea of reducing the dimension. You have 100 emails, and when you represent that in a 10-dimensional space, it is very sparse. Within that 10-dimensional space, if we ask how do we increase the density of this cloud, if we ask that question, the answer is, if we wanted to increase the density, then we need to collect more training data. Then only the density of the points will increase, because as you add more number of points, then we can reduce the chances of average distance. The sparsity can be reduced. But there is a downside. It is not that easy to collect more number of data for training. In many domains, it can be a very challenging task. it is not that easy to collect training data set for machine learning problems. So this issue of sparsity, which is introducing difficulty in coming up with decision boundary, or in case of regression problem, coming up with a best fitting geometry, is a challenging task that is referred to as the curse of dimensionality. Because as you increase the dimension, the sparsity of the data also increases, thereby imposing challenge to come up with a fitting geometry. So this scenario is referred to as curse of dimensionality. So solution is either you can increase the training data set so that the point cloud density increases. That is one solution. Another solution is we can somehow try to reduce the dimension so that we also end up with a dense cloud of points. So instead of using 10,000 features, if you could somehow reduce it to 1,000 features, increase the density, and solve the problem robustly. And if we think among, is it easier to collect more training data set, or is it easier to reduce the number of dimension, then we would stick to this, because the other one, trying to get more training sample, is challenging. Okay, so now reducing the dimensionality, it has two aspects. One is it helps in visualization, get a holistic understanding of the data. Second is reduce the complexity of our problem. There are two types of approaches mainly used for dimensionality reduction. One approach is called projection-based technique, and the other one is called manifold learning-based technique. In today's lecture, we are only going to look at a projection-based technique. We are not going to touch upon manifold-based technique. In projections, the prominent approach is called principal component analysis, PCA. And in manifold learning technique, the most popular approach is T-distributed stochastic neighborhood embedding, TSNE. Projection is a statistical approach in reducing the dimensionality. Manifold-based learning in TSNE, it uses a probabilistic approach to reduce the dimensionality. It essentially tries to preserve the probability distribution of the data, and it tried to minimize a cost function, objective function called Kullback-Leibler divergence. So that is the idea with the manifold learning. With projection, we are dealing with a purely statistical approaches, and it is more robust. The projection approach is useful in two aspects. It helps to reduce the it helps to reduce the complexity of the problem, and also it helps in visualization. But manifold learning, for example, this TSNE, it is predominantly used only for visualization. It is not used for the purpose of reducing the complexity of the problem. So this TSNE is purely visualization objective, but the projection based PCA has multiple objectives. It reduces the complexity as well as helps in visualization. So that is why it is more popular. So a three-dimensional data, what do we mean by projecting it? We find a hyperplane like this, and then we sort of project it. A three-dimensional data can be reduced into a two-dimensional data, and you can see the overall structure of the data is also preserved. So when we say from a three-dimensional data, we are reducing to a two-dimensional data, uh, we also preserve all the useful information. It is not kicking out one of the information. To quickly capture what do we mean by it is not kicking out, let us try to assume this. Look at these features x1, x2, x3. Let us call x1 as the age of the participant, for example, x2 as the weight of the participant, and x3 is the height of the participant. Let us assume we have three data like that: weight, age, and height, x1, x2, x3. When we say we are reducing it to two dimension, it doesn't mean that we are kicking out the height information or kicking out age or kicking out weight and preserve only the other two. If we do that, that concept is called feature selection. We are only selecting the features. But in feature reduction, what we are doing is that somehow we are uh, keeping track of all the useful information of all these three attributes and then reduce it to another set of features we refer to as Z1 and Z2. So in this place, we no longer call this as age, weight, or height. They lose that meaning. So Z1 does not represent age or weight or height. Similarly, Z2 does not represent that. This is some sort of a compressed representation dimension of the data. That is an important thing to remember. So when you reduce the dimension, the original meaning of the feature is lost, but useful information is preserved. This is a very important intuition to keep in mind related with PCA. So now, how does this projection-based technique, the PCA, works, the principal component analysis? So let me give you the geometric intuition behind how PCA works. So let's not read this. We can read this later. So what I wanted to mention is that let us assume this is uh, a small can. So this is a small can, and it is a three-dimensional object. In reality, a can is a three-dimensional object, and this photograph that we have taken is a two-dimensional image. It's a 2D object. So what has actually happened? So we have reduced a three-dimensional object into a two-dimensional object here by taking a picture. And now we are asking the question. So this is a picture of that can taken from its backside. This is the picture of the can taken from its front side. These are 2D representations of our three-dimensional object. This is a 2D representation picture taken from the top. And this is a 2D taken from the side view. So these are four different projections of our three-dimensional object onto a two-dimensional space. So this is the intuition. So what has happened? A 3D object has been represented as a 2D object. And now if we ask which of these projection contains the maximum information about the original 3D data. So if we look at these three, it has lost some information. It has not preserved the maximum information of the 3D data, but this side angle image has preserved the maximum information of the 3D object. So we get more information from this projection compared to other types of projection. This is the intuition what principal component analysis also trying to do. It will, given a higher dimensional data or even a three-dimensional can sort of thing, the PCA algorithm will find out in which of these directions, if we project, we preserve the maximum information. That is the core. It finds out that and then it will project it. This idea is called PCA. It's as simple as that. The intuition is very simple, though the mathematically how you do is there is a mathematical intensity there. But this is the intuition that we have to keep in mind. The idea behind principal component analysis. The technique finds out in which direction we should project the data so that maximum information is preserved. This is the important thing to keep in mind. So if we assume this simple two-dimensional data, we what it actually tried to find out is along which direction there is maximum variability of the data. Along which direction you can find maximum variation of the data. So if we look at that point of view, here you have a dashed line and a dotted line. Along the direction of this dashed line, we have maximum variation of the data being captured. So that is the essential idea. So it will find out the direction along which there is maximum variation and it will project it. And now we might have a doubt. What do you mean by projection actually? How do we even project it? We say that we find a direction and then project it. So mathematically, what is projection? How do we project? So I will run through an example, a simple example, so that even what is the intuition behind projection will also be clear. So when you look at that, then you will even wonder, oh, is it what we call as projection? It will be very simple. So let us wait for that moment. What do you mean by projection? So here, let me run through that intuition. So here we know along this direction we have maximum variation, and along its orthogonal direction we have its minimal uh, variation. Not minimal variation. What we do is that in a two-dimensional space we estimate two different directions, and these directions are going to be orthogonal. So if we find this direction and there is another direction that is orthogonal to it, these are the two directions that PCA will find out. And it also keep tracks of this additional information, that along which direction has the maximum variation, along which direction has second largest variation, third largest variation, and so forth. Here I am showing an example of two-dimensional data, so it will estimate two directions. One of that will have the maximum variation, and the second one will be the second maximum variation. That is what it will try to find. So now let us pick this direction along which we have the maximum variation and try to understand a couple of terminologies. We can represent this as a vector. This direction can be represented as a vector. So this is the vector I am showing here. So this is the vector that we are having. A vector, mathematically, we can represent it like this. This is the vector with the arrow on the top. AI plus bj, these are the bases, and this a b sort of represents the magnitude, or you can think of it like in a two-dimensional space, it is the coordinates a and b. So this is the pair a and b, Cartesian coordinate you can think of. So this is the vector representation. So it has a, so a vector quantity. So an important property to remember is that it will contain direction as well as the magnitude. These are the two properties that will define a vector. So we mathematically represent it. How do we find the magnitude and the direction? Direction, or we can also call it as angle. So magnitude is estimated as square root of a square plus b square. So this is called the magnitude of the vector. You can even think of it like it is the length of the vector. So that is the magnitude. We can find the angle of the vector by taking this tan inverse of this fraction b by a. The tan inverse b by a tells you what is the direction with let us say with respect to the x-axis, what is that particular theta, how much it is inclined. So that is the information that it keeps tracks of. So a vector has both the magnitude and a direction, the angle. So now if we take this vector and then divide that vector by its magnitude, what we end up with is something called a unit vector. So unit vector's length will be 1. So how for any vector you can convert it into a unit vector by dividing it by its magnitude. So we get a unit vector. And now the question, the magnitude between the original vector and the unit vector is different, but they share something in common. And if we ask what do they share in common, they share the same direction. Here only the length of the unit vector changes. Here the length was large, here the length is just 1 unit. But these two vectors, this v arrow and this v hat, this vector v and this unit vector, has same direction. So that is an interesting property. It preserves that. So the angle of, or the direction of the unit vector and the original vectors are the same. And now in this context, what is this vector capturing? Let us assume this is the vector capturing the direction of the maximum variation of the data. So that is this vector. So we took that vector and we decompose it into two. We decompose it into a unit vector, and we also know the angle, the direction of this vector. In the context of the principal component analysis, this magnitude of the vector, which is capturing the direction of the maximum variation, the magnitude of that vector is represented using the Greek term lambda, and this lambda is called as eigenvalue. So this eigenvalue is nothing but the length of the vector. You can think of it like the length or magnitude of the vector that captures the maximum variation. And this uh, angle that we have, this angle is preserved in this unit vector, right? So this unit vector encodes the angle of the original vector as well. So that unit vector that we deal with here, that is called eigenvector. So these two terminologies are important: eigenvector and eigenvalue. So these two jointly represent this particular vector actually, which gives us the information along which direction we have the maximum variation, and that is decomposed into a unit vector and its magnitude. That unit vector is called as eigenvector, and the magnitude or the length is referred to as the eigenvalue. So in a two-dimensional data, we can actually find two eigenvalues and its corresponding two eigenvectors. So one of that will be this, and the other one will be orthogonal to it. In a three-dimensional space, we can find three eigenvalues and corresponding three eigenvectors. So if we are dealing with a 10-dimensional data, we can find 10 eigenvalues and corresponding 10 eigenvectors. And these eigenvalue tells us about the variation of the data or the maximum variability. So the eigenvalue with largest value tells us the maximum variation. There will be another eigenvalue which is second largest. That tells us in which direction you can find the second largest variation. A third eigenvalue tells you the third largest variation, and so forth. So if you take eigenvalues and sort it, you know along which all directions you have the maximum, second maximum, third maximum, and so forth. So that is an interesting property which principal component analysis makes use of. So given a two-dimensional data or 10-dimensional data, now the question is, how do we find the eigenvalues and eigenvectors? We won't get into the mathematical derivations, but due to time limitations, we can't go that in depth. But let me tell you the intuition that these eigenvalues and eigenvectors are estimated using a technique called singular value decomposition. So it is essentially a matrix factorization technique, and using the singular value decomposition, we can find out the eigenvalues and eigenvectors, which essentially gives us the information about in which all directions we get the maximum variation, second largest variation, third largest variation, and so forth, based on which we will project the data. So now what we need to understand is what do you mean by projection. So let us try to understand a couple of terminologies about what do you mean by variance, covariance, and the covariance matrix. So variance essentially gives us the information about uh, if you take variance of a particular random variable, it tells us what is the uh, spread. It's a measure of the spread. That means it tells us the sparsity information. If the variance is 0, that means all points coincide on lying on top of the other. If the variance is very small, that means all points are very much similar. But if the variance is high, then the data are spread apart, they are sparse. So that is the idea that we infer by looking at the variance. Even in the previous class when we were discussing about data normalization, I was also mentioning about how you can infer this by looking at the standard deviation. So when you just square the value of standard deviation, you get variance. That's how they are related. So by covariance, what we mean is that we take two different variables, and then the covariance essentially tells us how x and y are related between each other. So that is what covariance is. When you find the covariance between x and x itself, then it becomes the variance. So it finds the relationship between x and y, how correlated. You can intuitively think of it like how correlated x and y are. So if you are given three attributes, you can come up with a 3 cross 3 matrix. So if x1, x2, x3 are the weight, age, and height information, then you can find covariance between height and height, covariance between height and weight, covariance between height and age, and so forth. So this is what. So it will be symmetric. Covariance between x1 and x2 and covariance between x2 and x1 are same. So if you have a three-dimensional data, we can end up with a 3 cross 3 covariance matrix. This is another important result to keep in mind. So if you take this as example, x1, x2, x3, if you have 4 samples corresponding to that, but still you will end up with a 3 cross 3 covariance matrix because you are dealing with 3 dimensions essentially. So you can end up with a 3 cross 3 covariance matrix, and you can see that the other off diagonal elements are symmetric. It can be actually estimated using these numpy operations. So if you represent these numbers, you can actually estimate these covariance matrix. I'm just showing this quickly, but let us run through an example. So our example is, how do you reduce a two-dimensional data into an one-dimensional data? So that's what we are trying to calculate. We need to uh, sort of reduce our 2D information into 1D information such that all the informations are preserved. We are not kicking out, but we use PCA to estimate how do we find this projection. So let us assume this is our two-dimensional data that we are going to deal with. So x1, maybe it is the weight of the participant, x2 is the age of the participant. Let's assume a toy problem like that, x1 and x2. This is what we have collected. And we need to reduce that into an one-dimensional data. The first what it will do is that it will find the average of all the 10 values of x1, the average of 10 values of x2. So you will find the average of x1 and x2 separately, and then we do a mean shift. That means you subtract the mean. So if 1.17 is the average value, the mean value of all these 10 numbers, then you take that mean and you subtract it. So what you will end up with is a mean shifted data. So we subtract the mean to x1. Similarly, we apply the same operation to x2 as well. If 1.3 is the average value of x2, then we take that and subtract it here. So now we get a mean shifted x1 and x2. For these x1 and x2, since it is a two-dimensional data, we can end up with a 2 cross 2 covariance matrix. And from these 2 cross 2 covariance matrix is where we find the uh, eigenvalues and eigenvectors that we mentioned previously. Say, for example, we can estimate. So there are techniques by which we can find the eigenvalues and eigenvectors. So let us assume from this covariance matrix, we estimate the eigen values and eigenvectors. So so we already looked at the intuition behind what do you mean by eigenvalues and eigenvectors. Let's say we have two eigenvalues. Eigenvalues are nothing but the magnitude of a vector. So here we have two magnitudes. 1.250 is a magnitude, which is an eigenvalue. 0.034 is another eigenvalue, with nothing but magnitude of another vector. So we have the magnitude of two vectors. And now if we ask what is the eigenvector corresponding to this magnitude? Corresponding to this magnitude, the eigenvector is this column vector. So if you have an eigenvector matrix, the first column represents the eigenvector, or this is a unit vector. So this is the eigenvector corresponding to the eigenvalue 1.25. Look at this column. So this is the eigenvector corresponding to the this particular eigenvalue 0.034. So now you have two eigenvalues and two eigenvectors, which we interpret it as column vectors. So now the question is, we need to reduce two-dimensional data into one-dimensional data. So now projection has to happen. So now this is our two-dimensional data, which is nothing but the mean shifted data. So we estimated from the original attributes, we found out the mean, and then we subtracted the mean to all the values. So this is the mean shifted data. So this is two-dimensional. And now the question is, we need to project it, or we need to get one-dimensional representation of this data. For that, what we have to do is, the approach is this: pick the eigenvector corresponding to the largest eigenvalue. So the largest eigenvalue is 1.25. Its corresponding eigenvector is this column vector. So let us take that column vector and put it here. So we have this column vector, put it here. So now if we look at the uh, dimension of the matrix, we have 10 entries, 2 columns. So this is a 10 cross 2 matrix. If you look at the dimension of this eigenvector, it is a 2 row 1 column. So it is 2 cross 1. So now we have a 10 cross 2 matrix and a 2 cross 1 matrix, and we can obviously multiply them. So if we multiply a 10 cross 2 matrix with a 2 cross 1 matrix, what we will end up with is a 10 cross 1 matrix. So we will end up with a 10 cross 1 matrix. So this, taking our original data and multiplying it with the eigenvector, is essentially called as projection. So projection is nothing but a straightforward matrix multiplication only. But to what we apply it, so we have a specific name called projection. So that's it. So we took this, and we took only the first data and we first eigenvector, and we did the matrix multiplication. Let us assume if we had 4 attributes. If we are dealing with 4 attributes, we would have a 4 cross 4 covariance matrix, and we would have 4 eigenvalues and 4 corresponding eigenvectors. So depending on the dimensionality of the data, that many eigenvalues and eigenvectors we will have. So that is an important point to remember. So in a 4-dimensional matrix, if we ask, reduce it into a 2-dimensional data, a 4-dimensional data into a 2-dimensional data, in that case, what we will do is pick the 2 largest eigenvalues and pick its corresponding eigenvectors. If we say reduce it into 2 dimension, then we have to go to the 2 largest eigenvalues, pick its corresponding eigenvectors, represent that in a matrix, and then do a matrix multiplication that will reduce it. So if you had a 10 cross 4, and this, if you are picking in as 4 cross 2, then that will reduce it into a 10 cross 2 matrix. So this is the essential intuition or the working principle behind the dimensionality reduction that we need to keep in mind. How does dimensionality reduction work? So the singular value decomposition that I was talking about is about this matrix factorization, but those intuitions and things, we cannot explain it in a short lecture. We also will get into feature selection procedure as well. So this is what essentially the technique that I wanted to. So this you have to keep in mind. So this will help you in terms of thinking in terms of dimensionality reduction. Find the eigenvalues and eigenvectors. So these eigenvalues and eigenvectors are nothing but telling you along which directions you have the highest variation, the second highest variation, third highest variations, and so forth. So if when you wanted to reduce it, you pick the uh, largest variations and then reduce it accordingly. So that is what we need to we need to do. The reducing in the sense we are projecting. Projection is nothing but matrix multiplication. So this is the essential intuition that I wanted to mention. And this is a very prominent approach that we use in terms of reducing the complexity. And no matter whatever be the higher dimension, if our purpose is to visualize it, you can always pick the three largest eigenvalues and its corresponding eigenvectors and perform these projection. You will always end up with a three-dimensional representation of the data, which you can visualize it. Even if your original data is 100 dimension, doesn't matter, 100 or 1000 dimension doesn't matter. You can pick the three largest eigenvalues and its corresponding vector and multiply it here. You will reduce it into a three-dimensional data. And that three-dimensional data is sort of preserving all the useful information of all those 100 or 1000 dimensional original data. That is the intuition we need to keep in mind as well. Okay. So now, how do we use scikit-learn to perform dimensionality reduction? That is one thing we will look at. And secondly, we are going to also look at how do we perform feature selection. So this is one approach. Sometimes some feature selection techniques can also be helpful. When do we prefer one with the other? There is no straightforward answer. This all has to be experimentally found out. So you need to conduct experiments using both dimensionality reduction as well as dimensionality selection. So dimensionality, you can synonymously call it as feature. So feature reduction or feature selection, and then see which one helps. So whenever you are touching a machine learning experiment, always take it for granted that you will spend a significant amount of time running several experiments. And as a machine learning researcher or an engineer, your task is to run several experiments and pick the best, infer and pick the best from that. So this is what we need to understand about machine learning experiments in general. So now what I wanted to show you now is about dimensionality reduction technique. Okay. So can you please confirm whether you can see the collab code that I'm showing here? Yes. Okay. Okay. Thanks. So here I'm going to just explain how we can reduce the dimensionality of the data. So I'm going to use another publicly benchmarked data set. It's a breast cancer, Wisconsin diagnostic breast cancer data set. It is a very popular data set, has been widely used in research publications prior to all these deep learning revolutions. So now, since we have more number of medical images corresponding to breast cancer, then you can straight away apply automatic feature extraction. You can run, for example, convolutional neural networks, try to extract features automatically, do classifications like benign or malignant. So these all are the current trends that is happening straight away on images. It could be mammogram images or histopathology images. We are not talking about that. These are some attributes related with a patch, and then uh, we are based on those attributes. The task is to classify whether it is malignant or benign. So that is the original problem statement. So you can read up if you're very much new to this. You can read up about the breast cancer data set that will give you information. So what I am showing is you can load the breast cancer dataset that comes as a pre-built package within the scikit-learn's dataset. There are several benchmark dataset that is available within the scikit-learn. Previously, also we saw one example of using the iris flower dataset, which contains 4 attributes. We saw that for the non-parametric approach, the decision tree, and all those bagging and boosting, we just took that as a running example. Here we are taking this breast cancer data set. This is a 2+ classification problem. So it's a binary classification problem originally. The task is to classify whether input is a benign or is it malignant. These are the two things to pick up, classify. We are loading this data set. We can additionally pass this argument return x underscore y is equal to true. What it will do is that it will process the data such that we will get the attributes, the input attributes in X and the target attribute values in small letter y. And it is also very standard practice, machine learning programming practice, to use capital letter X for your inputs and small letter y to store your ground truth output values or target or labels, whatever we call it, so that we store it in small letter y. This is a general convention. And general convention, is there any mathematical significance? The fact is that here x can be multidimensional, but y is always univariate. So that is the reason why usually we put it as capital X and small letter y. Even linear algebra terms, we represent scalar values as small letter, but a vector using these capital. So that is the logic behind that. But there are no strict rules. You can name it whatever name you want. It doesn't matter. So we can look at the shape of the data. When we are loading these data, they are actually of NumPy array. So let me just connect it. So you can also look at what is the type. So you can, if you want, you can infer it. So if you look at the type of this X, it will be a NumPy array. So we are essentially looking at the shape of the NumPy array. So just by looking at the shape, we get, let me just quickly run it. So here we are looking at the shape of this matrix, which is 569 rows and 30 columns. This type of tabular data, they are usually referred to as design matrix. So let me just print also additionally what is the type of X. So if we print what is the type of X, it should say NumPy array. So you can see it's a NumPy n-dimensional array. That is the base class for these kind of numerical arrays. So this 56930, it is a two-dimensional matrix. So these X are usually referred to as design matrix. So that is another name that people use, design matrix. Our input matrix. And now our task is, it is, so what we should interpret from this is that we have 569 samples, and so that is the number of rows, and 30 attributes. This is the number of columns, and this is always the convention. The column represents the attributes, the row represents samples. So the number of rows tells you how many samples you have in your problem, and the column tells you how many attributes you are going to deal with. So there are 30 attributes for this particular problem. And let us say we don't want to deal with all the 30 dimensions. Maybe some of the dimensions are redundant, or maybe something is unnecessarily introducing complexity to the problem. So we might need to reduce it. We wanted to try and reduce the number of dimensions and see whether that is giving us a better performance. To try that, what we have to do is we have to call the PCA class. PCA is a class that is defined inside the scikit-learn's decomposition underscore components is equal to 10, it means that we want to reduce our data into 10 dimensional data. Doesn't matter what your original data is, how large it is, we want to reduce it to a uh, 10 dimensional data. So PCA is the object, and now we just fit, we call a fit function, and we pass our x. X is our input data. So inside this x, if we ask what happens inside this x, inside this fit function, this is what the intuition I was explaining previously. So for all the 30 attributes, it will find out the mean, it will perform a mean shift, and then it will estimate the covariance matrix of your 30 dimensional data. So we will end up with a 30 cross 30 covariance matrix. From that covariance matrix, using singular value decomposition technique, we estimate 30 eigenvalues and corresponding 30 eigenvectors. So we will have these 30 different directions that captures in a decreasing order. So the direction of maximum variation, the direction of second largest variation, third largest variation. Likewise, there will be 30 directions that we estimate, and those directions are called those directions are encoded in a unit vector, and those unit vectors are referred to as eigenvectors. So, and there will be corresponding eigenvalues as well. So that eigenvalue tells us how large it is. A particular eigenvector, how large it is understood by looking at its eigenvalue. So that is the magnitude. So when we call fit, it is estimating 30 eigenvalues and 30 eigenvectors, because we are dealing with 30 dimensional data. And now when we say PCA dot transform, when we call this transform function on this x, what it will do is that it will pick the largest 10 eigenvalues. It will pick the corresponding eigenvectors. So there are 10 largest eigenvalues. We are picking its corresponding 10 eigenvectors, put them in a matrix, and now perform a matrix multiplication between our original 30 dimensional data and our 10 and our 30 cross 10 dimensional eigenvector. And once you reduce it, you will end up with a 10 dimensional data. So when you look at what is the shape of these PCA transformation, we will see now it is a 10 dimensional data. Previously, it was a 30 dimensional data, and we were able to reduce it to a 10 dimensional data. If our purpose was to visualize it in a 3 dimension, then you can just, instead of 10 here, you can just remove it and put 3, and if you run it, you will end up with a 3-dimensional data. Then using matplotlib library, you can visualize the 10-dimensional, the 3-dimensional data, how it looks like. And this 3-dimensional data encompasses or captures all the useful information of the 30-dimensional data. So that is the intuition we should have for this PCA. Here I just preserve it as 10. So this idea is dimensionality reduction, preserving the useful information. Useful information is found out by the maximum variation. So this variation direction is the information that we are talking about. So now we need to enter into feature selection. So this is the reduction technique, but we can also try out feature selections and see whether that is helping. We cannot always guarantee that reduction is the only best approach. Reduction is one of the popular approach, but we could also try selection procedures and see how it performs. So if you think in all, when you want to conduct analysis for your experiments, then there are so many different possibilities that you should do. And this is what even in industries, for machine learning engineers, their task is to run all these experiments. This is what they are paid for, and they should know what are the experiments to do, how to call the relevant library functions and run it, obtain the results, and even perform data analytics on the results and so forth. This is what machine learning engineers in industry predominantly do. So now coming to feature selection, I'm going to discuss some of the important techniques that can be used in terms of taking a subset of the features. Say, for example, we are going to run through the same data set where we have 30 features. From that 30 features, how can we select certain features? So one of the techniques, a simplest technique, is performing variance threshold. So what it means is that you have 30 columns. For each column, we can find for each attribute, say for example, let us name the attribute as x1, x2, x3 up to x30. So x1 is a collection of 569 samples. x2 is a collection of 569 samples. What we can do, for x1, we can find the variance. So that is the square of the standard deviation. So we can find the variance. For x2, find the variance. x3, find the variance. So for every attribute, find the variance. If the variance is above a certain threshold, then we decide to retain those features. Otherwise, we would discard the feature. So this is one simple strategy that you can apply to discard the data, because if the data do not have good variation, that means the variance value, or do not have good standard deviation, they all are very close enough data, they're very dense, that doesn't add too much of robust, that doesn't act like a robust feature, because that feature is not highly varying. So you do not get useful information from such attributes. That is the idea behind taking this decision, variance-based thresholding, to kick out certain features. So what features to kick out? So feature selection is about kicking out the dimensions, not taking any useful information from that. You straight away kick it out. So now for variance thresholding, there is also a class defined inside scikit-learn, which is defined inside the module feature selection. So from that, we are importing this variance threshold. And for that variance threshold, so here I am just doing it in a simple computation. So we are calling that variance threshold, and we are specifying a threshold value as 20%. That means if the variance is above, if it is more than 20% variance, then we retain it, otherwise discard it. So if we do that, so here there is a function called fit underscore transform. So in scikit-learn, you also see fit underscore transform. So here in the PCA part, I did a fit separately and then performed transform separately. What we can do is we can do both in a single operation, which is called fit underscore transform. This is a very handy, convenient function provided in scikit-learn to achieve such task. Instead of doing it in two steps, you can just achieve it using one particular call. And I am passing this 30-dimensional data, and I am collecting the reduced in the sense the selected features in x underscore. I name it as VT because just to distinguish that it is a variance threshold based selection. And now when I print the shape of that variance threshold, now I see that it has retained only 11 dimensions, 11 features, and it has kicked out the remaining 19 features. Because all those 19 features, the variance was less than 20%. So we just removed it. So this is one simple approach to kick out the attributes. And I'm essentially going to discuss about 6 different approaches for feature selection. So variance threshold is one. So I'm sort of explaining it in sort of an increasing complexity of feature selection. This is the simplest variance threshold. There is another approach called selecting the k best features. So there are some sort of ranking involved, and then it is selecting the k best features. When we are doing this selection procedure, there is a pre-built ANOVA approach. There is another analysis of variance approach called uh, F underscore class if defined inside the scikit-learn. It is an F test technique from statistics. And what does F test do? It is trying to find a degree of linear dependence given between any two random variables. So given any two random variables, how much linearly dependent two attributes are. So here it is essentially talking about features. So it will find out how it's a measure of how much dependent two variables are, based on which we perform the selection. So if two variables are highly correlated, for example, we don't need to actually keep those two variables. Instead, we can only keep one of that. If x1, x2, and x3, all these three are highly correlated, then there is no use in keeping all those three, but rather use only one of that. So they just can just pick one of that x1 and remove x2 and x3. So that is the intuition. So that is what the select k best will do. So inside the feature selection, so now whatever I am explaining, it is all defined inside the feature selection module. So you can go to this feature selection and call this select k best using this f test measure. So we are calling this f classification, that is our scoring function, and we are saying select the 16 best features. So we can call the fit to transform. We use the x and y. So here we also need to pass the y label as well. And then it is picking the k best attributes. And then we can look at it is a 16 dimensional data, because we explicitly mention what is the value of k. So here we have to do that. But in a variance threshold, we are only specifying the threshold, and the number of features is dependent on the threshold. But when we are coming to this k best selection, we have to explicitly specify this k. But that is a hyperparameter, and it is a challenge. Even say, for example, you wanted to do a k-means clustering, group together into k clusters. But the downside is that you should already know what should be the best k. Even though there are some iterative, computationally heavy procedure to find what is the best k for a given data set, but it is all computationally intense. There is an approach called elbow technique to find what is the best k. So likewise, we don't have any very good strategy here, but here we need to explicitly say the value of k and then run the experiment. So for several different possible values of k, we need to run the experiments and then analyze how it is performing good. So this is another challenge. We can even consider using hyperparameter tuning for this as well, so that it will automatically find out what is the best k. So here is the k-best part. There is additionally another approach, something similar to threshold. It is about select percentile approach. So here we are saying, talking about the highest scoring percentage of features. Say, for example, we are saying pick the highest scoring 25% of the features. Even though this is a percentile, is a relative ranking, based on that relative ranking, we are saying pick the best 25% of the features. So here also we perform this fit transform with xy. We do this select percentile. So this is the 25% of the best features. And with this 25 as the attribute, we get 8 features. So 30 dimensional data. From the 30 dimensional data, we pick only the 8 best features. So this is essentially good as compared to this, because we are picking only the best, and we have some explicit control based on we are picking the best 25% or best 30% and so forth. So these are some simplest approaches. So there is another approach called recursive feature elimination approach, which is defined inside the feature selection technique. So what it will do is that we have to explicitly define a classifier model. Say, for example, we call support vector classifier, and we can call it a linear support vector classifier, for example. and this C is a regularization factor. So let us just put it as a default value of 1. So we have, what essentially we need is we need an estimator. So for this recursive feature elimination, what we will do is we will apply or pass a classifier, and then we say you start with all the features initially, and then try to keep on. So here when you say step is equal to 1, what it will do is it will keep on removing one feature from the entire data set, and then it will keep on looking at the performance of our classifier, and then it will pick 8 features that is giving the best performance. So that is what here the recursive feature elimination does. So it will start with 30, and then it will remove one after the other and eventually find out 8 best features that is best performing. So this is the idea behind recursive feature elimination. The only additional challenge is that we have to explicitly provide an estimator. So it can be a support vector machine, it can be a softmax or a logistic regression model, it can be decision tree, random forest backing. It is left to us. So here is just showing an example of using a support vector classifier. So you create an object for that and you fit it. This is what it will do from that selector. So you can also look at what is the, so here you have 30 attributes which has got a rank. So it is the ranking. So when you put 8 as the number to select, then it will put the top performing 8 features as rank 1, and the remaining will be ranked appropriately, 2, 3, 4, and so forth. So the first 8 top performing features will be given rank 1. And if you just apply a transform on X, it will only pick those 8 features. So now you will end up with an 8-dimensional data. Originally, this X was a 30-dimensional data. You now end up with an 8-dimensional data, and we kick out the other 22 features because that is what the support vector machine's performance suggested us. So that is one approach that we can do. Here, for example, another approach is using the L1 norm. So this is specifically for the linear models. We don't do it for nonlinear models, but this L1 based approach is used for feature selection. When we talk about regression, so if we discuss about model overfitting and regularization techniques to overcome this overfitting scenario is where the model's training performance is very good, but the testing accuracy is very bad. Such a scenario is called overfitting. That means the model is not generalizing. It is only trying to learn its training data set, but it doesn't generalize to data it has not seen, namely a testing data set. So there are approaches called L1 regularization and L2 regularization techniques. In terms of regressions, they are referred to as L1 is referred to as lasso regularization, and L2 is referred to as ridge regularization. So these are two standard terminologies. So that comes from the theory behind machine learning model regularizations. So we can use that L1 regularizations, which is lasso. Lasso stands for least absolute selection operator. So least absolute selection operator. So that's what this lasso stands for. So that's where we are doing this L1 norm. So how to perform that? So say for example, we are using a linear support vector classifier, and there is a functionality called select from model. So we can set the attributes for this linear support vector classifier and specify the penalty or the regularization to use is L1. And when we do such sort of thing, especially for support vector machine, we have to specify this dual as false, because this is the technique by which for support vector classifiers it is trying to maximizing the margin. So there you have to specify the dual approach as false. That is what by default it expects. Why so, I don't know specifically, but that is how they have implemented. So if you wanted to perform such L1 based sparse representation, you shouldn't be using this dual approach. That is what recommended. So once we have that, using the select from model, we can pass our support vector machines and use this pre-fit. So whatever we have fit here using the X and Y, we're using that. You can actually look at the reduced features. So that is giving us suggestion that these are the 6 features out of the 30 features that is best performing. So this is based on the L1 regularization or the penalty, or the L1 regularization that we can do this. The intuition is that for linear regression, we saw that there are coefficients like theta 0 plus theta 1, x1, theta 2, x2, theta 3, x3, and so forth. What L1 regularization does is that if a certain feature x3 is not very useful, then its coefficient theta 3 will become 0. It will set it to 0. That is how we are kicking out a particular dimension. If x5 doesn't seem to be a useful attribute, then its coefficient theta 5 will be set to 0. So that is what this sparse solution means. So that is what this lasso regularizer does. So that this is one way to perform feature selection. And the last one that I would like to explain is a tree-based feature selection. So it is based on the Gini impurity criteria that we discussed for CART algorithm, the classification and regression tree algorithm, which is a greedy algorithm which grows the tree such that its subchild has the tendency to generate a Gini zero leaf node. So that is the objective behind the CART algorithm. So based on that criteria, these CART algorithm can also find out which features are useful in for classification and which features are not very useful in those decision making. So based on that importance, certain features can be discarded. So there is the specific more class called extra trees classifier. So this is specifically used for feature selection, which is defined inside this ensemble, and you can use this select from model is the approach. So use the decision tree. We are using 50 decision tree classifiers, and we are fitting that classifier, and for that we can estimate the importance of the feature. So if you have 30 attributes, it is telling you the importance of those features, and based on those importance we can select the important attributes. So that is what this select from model will do from this tree classifier, which is already being trained. That is what this prefit is equal to true says, which is already being trained. From that, we can apply the transformation. That means feature selection on this X based on the top features. And when we look at it, it has implicitly taken only 6 attributes and says that these are the 6 attributes which are useful for solving the problem. So these all are feature selection techniques where we straight away kick out the attributes. And the initial one that we saw is the dimensionality reduction technique, which is not kicking out, but it is somehow preserving the useful information. Even if a certain dimension seems like highly irrelevant, it will try to capture some useful information from that data and dissolves it into the lower dimension. That dissolving into lower dimension is essentially the projection that we do onto the eigen vectors. So this is what essentially we need to understand about feature reduction and feature selection, and I hope that this will be useful for your experiments. You should also additionally try this and see how these helps in solving your problem. There is no, see, that's why in machine learning there is a common usage adage saying that there is no free lunch So the free lunch theorem says that there is no one particular approach that is best for all types of problems. So that's what in machine learning, when they say no free lunch theorem, that's what it means. There is no one particular approach that is universally applicable to all. So we need to experimentally try for specific problems and find out which approach is good. Even we said in the last lecture, I mentioned that gradient boosting is rank 1 because it is performing extremely good on all complex nonlinear data sets. Even if your data set is humongously large, decision trees can handle it. We also mentioned that support vector machine is also an extremely powerful approach, but there is a small challenge to support vector machine, that if the data is humongously large, then support vector machine will be very slow, and sometimes it cannot find optimal solution. There is a challenge. But if the data set is, say, in the order of 10,000, training data set is in the order of 10,000, then support vector machine is good. It might even outperform sometimes gradient gradient boosting technique as well, or even random forest technique as well. But you have to, but again, that's what we say by no free lunch theorem. So you have to find out. So by saying gradient boosting is rank 1 doesn't mean that all other approaches that has been developed in machine learning is obsolete. So that is not true. Sometimes some other approaches might outperform, say for example support vector emission. Sometimes kernel support vector emission with the radial basis function, that kernel might outperform other approaches as well. But for that, you might also need to find out what is the best parameter. You need to find out what is the best regularization parameter C, or even for radial basis function, we are using that Gaussian kernel. So the Gaussian is defined based on mean and standard deviation. So standard deviation plays an important role, the width of the Gaussian. So that is controlled by a parameter called gamma. So what is the best combination of C and gamma that outperforms? So you need to perform hyperparameter tuning there. So what I wanted to say is that even though there are approaches like support vector machine, random forest, or gradient boosting being rank 1, if we ask the question, why do we need even other techniques? So that is justified based on a philosophical precept called Occam's razor principle. So you might quite often encounter this terminology, Occam's razor principle, in some classic textbooks, or even in some research papers, people mention that. So what does Occam's razor principle suggest is that it is a scientific precept which says all things being equal, choose the simplest one. That is the scientific precept behind Occam's razor principle. All things being equal, choose the simplest one. In this context, what does it mean is that for a specific problem, if there are multiple techniques that leads to same performance, choose the approach which is simplest. Say for example, logistic regression is giving 98% accuracy for classification. Gradient boosting is also giving 98% classification accuracy. Then go for logistic regression, because logistic regression is the simplest approach compared to gradient boosting.